All right, I'm on 52 weeks of interesting languages, and I'm on Julia still. I may switch to a different language soon, but for now I'm still on Julia, and I have Control Flow is on my agenda. I'm going to go ahead and share my screen, get into here, and take a look at Control Flow. All right, so I guess if we look at Julia here, it's got some of the same things you would expect, if else, that kind of stuff. It's got the bash type or shell operators, ands and ors, and it's got while and for, and we have try catch, and we also have coroutines like Python, like yield. So the first five are standard in languages, right? 1, 2, 3, 4, 5. Tasks are not so standard. They provide non-local control flow, making it possible to switch between suspended computations. So interesting. Yeah. Well, let's try this out first. Compound expressions. I guess here we have a begin, x is equal 1. So sometimes it's convenient to have a simple expression which has sub-expressions inside of it. Well, let's try that out. So I'm going to go ahead and go back here to Julia, spin it up in a code space, which is one of my favorite ways to play around with things. I guess I could also do Julia in SageMaker Studio Lab, actually, which is a great environment for doing things. But yeah, so we got Julia here. And if I go ahead and we'll call this, episode 5. Perfect. So let's go ahead and do Julia. They're talking about concept of a begin, which is interesting. Here's an example of a begin block. Never used that concept before. And then they just do like x is equal to 1, y is equal to 2, x plus y. Okay, so x is equal to 1, y is equal to 2, z is equal to plus y, something like that. And then how do they do? They do the end. They just do it. I guess they tab these over though, which is interesting. End. There we go. Interesting. So it's like a sub-statement. I'll have to really think that through. That's an interesting concept. So I'll put this inside of here just to look at this again. So we'll call this compound expressions. Okay, so Julia, compound expressions. And why would you use that? So it's useful to have an expression which evaluates sub-expressions in order, returning the value of the last one. So if I say z, what do we get here? I guess it's kind of like a mini function. It's like a function that you don't have to define, I guess. I mean, it's an interesting concept. I've actually never come across that. So these are fairly small. They can be placed into a single line where the semicolon comes in handy. Okay, so you can just, which is kind of similar to Python, you can chain things together, right? Like you can do similar things. In fact, I could compare. So if I just typed in, is IPython here? There you go. So if I wanted to do that exact same piece of code, what happens? You have to do in Python, you could do this, I believe, without the brackets. Z is equal to x. Yeah, so you can do the same thing in Python with, and in fact, you can also do that with one-liners. You can say Python -c import os.lister, something like this. This is kind of a hacky thing to do. I don't know why you would do this exact one-liner, but and you could even do prints that. There you go. Interesting concept, though. The syntax is useful when they're terse function definition forms that you want to use. So you say begin, end. I see. Like that. Okay. I'll have to look at that later in a little bit more detail. I'll put a note to it, though. And we'll put a note here. Maybe add, like, I'll put my example here in IPython. Just say something like similar to Python. Right. Do this. What else? Conditional evaluation. So yeah, this is pretty standard. A lot of languages have this. Some languages don't use it often, like R. It's kind of hard to find many examples of people doing conditionals. But we'll go ahead and just put this into Julia. There you go. If X is less than Y, X is less than Y. Okay. Useful. Now, we also have the concept of functions. Function tests. I see. Generic function. In this case, what is getting returned? Nothing's getting returned. But we're just building a function we can use. Okay. So let's try that out. So we got a function called test. And so we just say test 2 and 2. X is equal to Y. 2 and 3. X is less than Y. And we can say 4. X is greater than Y. Okay, pretty intuitive. If blocks are leaky, they don't introduce local scope. That's interesting. Okay, so what do we got going on here? The so-called ternary operator is closely related to the if else syntax. So it gets its name from being the only operator in most languages taking 3 operands. The expression A before the question mark is a conditional, and the ternary operator evaluates the expression B before the colon. The easiest way to understand this is the example. So let's try it out. So we got X is equal to 1, Y is equal to 2. Let's try that out. Okay. Next up, we print this. Okay, makes sense. Prints. I see. So there's 3 different evaluations here. What happens here? And then you do this. X is equal to 1, Y is equal to 0. And we'll do the same thing. And this not less than. Okay, so what's going on? If the expression X is less than Y is true, the entire ternary operator evaluates to the string less than. Okay, so if this is true, then that's what happens next. Otherwise, it evaluates to the string not less than. The original 3-way example requires chaining multiple uses of the ternary operator together. So in this case, you could do this. You could do this. So you could chain lots of them together. The operator associates from right to left. It's significant that like if, else, the expression before and after the colon are only evaluated if the condition evaluates to true or false. Interesting. So yeah, those look like they're kind of fun to play around with. So I'll just put a note to that. Is there a note to this? Yeah, maybe I'll add a little note like ternary operator is fun to play with. So yeah, that's kind of a neat little thing to play with. Add that. And then add copy address. There we go. Perfect. Okay, next step, you've got the short circuit. So I do have a fondness for short circuits, and so let's add that next. Short circuit. Oh, circuit. So these correspond to the and or, which I use a lot in Bash, Makefiles, those kinds of things. And the idea is that it's a conditional expression. So we can make a function true, I see, and then make a function false, a true and a false function, and then you play around with it. Okay, that's kind of an interesting concept. So let's do that. We'll go here, got a true, and we'll do false, and then you can start playing around with the short circuits. So we can just say, in fact, T1, you say, and, so only run the second part if the first part is true. In this case, it will run the first one. The second one, it prints it out, but it returns back false. So if I wanted to add another condition, and I said T1 or T4 won't run. It stops. This does not evaluate to true. But what we could do is we could check out how their OR works next. So we got all that. So what does this do? Oh, I see. So either do, so the OR, how does this work? So some languages refer to them as and or. The reason that and must be false if A is false, and likewise, but A has a higher precedence than or, so it's easy to experiment. So in this case, let's use T is equal to true. So only the first one goes. So in this case, if I run this, it says either or, but since that one's true, we don't need to go further. But if I change it to F, the second one would run. Although the first one runs and the second one runs. So basically, which is interesting. Yeah, so the or, I have to admit, I don't actually use that often. And so I'll probably play around with that a little bit. So it looks like you can do some cool stuff with it. Boolean operations, repeated evaluation of loops. There are two constructs. Okay, so the while. So now we're moving on to while loops, global. So this, we have a counter right here that's initialized. And then we say while the counter is less than or equal to 5, go ahead and print it out, and then go up one level of scope and increment that counter. So this is pretty traditional programming stuff here. So we'll put this in there. We'll add a loop. So short circuit, while loop, and add that in there. Copy this link. There we go. So let's try this loop out. We'll do, fortunately, it's pretty concise code. Right? We don't need to do much. We just need to say while I is less than, while I is less than or equal to 5. We don't even need to do a brackets or anything. We can say print it, right? Print line. So that's intuitive. Print ln I. So the first loop will be 1. And then we'll say global. Is it just global by itself? It's yeah, global, and then we do an increment. I plus e. And then do I have to end it? Yeah, I have to do an end. So then I go here to end. There you go. And we can see as well that yeah, everything's pretty intuitive in that particular example. I guess I could just throw this into here and say, Julia. Pretty intuitive. There we go. I'd be curious to test the difference in speed of both in Python versus this. I'm going to do that. Let's play around here a little bit. I'm just curious. A tight loop in both languages. So let's exit this temporarily. We'll make a directory called benchmark. Oops. And so I'm going to cd into there. I'm going to make one called while Julia.jl, and we'll make one Python.jl. So now I'm going to go, I'm just going to just tweak this a little bit, and we'll do while Julia, whoops, move while Python to while Python with an extension. Okay, so while Julia, let's do 500 and take away the prints, because that might give us a false sense of confidence. And I'm going to type in time. I'm going to do while Julia, or say time Julia. And that took 0.2 seconds. Now let's do the same thing in Python. And let's open this up, and we'll say while x is less than or equal to y. We can do something similar here. We can say let's say example x is equal to 1. And say y is equal to wait, let's make it kind of apples to apples. Yeah, so we'll say x is equal to 1. We'll do this 500. and we'll say x plus 1. There we go. So it's a pretty tight loop as well. Time Python while Julia, or while Python. So slower. Interesting. That we see that there is a performance boost in Julia versus Python. I mean, I guess I could change it to like to 50,000. Let's try that out. Wow, interesting how that the 50,000 didn't even make a big difference. So 50,000, 100,000, 1 million, 5 million. Right. So this would be 1, 2, 3. Yeah, 5 million times. Okay, let's try it out. Okay, we're back here. Not sure why the sound went away for a second, but the if we go ahead and look, if we look here, that this for loop that we can do 5 million. So 3 here, 1, 2, 3, 1, 2, 3. So five. We have 5 million. I don't think we want to print this though. Just want to. Well, why not? Let's see what happens if we print it out. and we say Julia or Julia. It takes a while, maybe too long. Maybe what you want, like if I'm gonna print, let's take a few off. Let's just go to 50,000. That's probably better. Let's benchmark that. So how do we go? How long does it take? Let's time it, and it takes about a second. So we'll put a note here. I'll do the same thing in Python. Python. And we can do something pretty similar in Python. We can do for I in range 1, 2, 1, 2, 3. We can just say print I. So kind of similar. If I time it, Python, F4, Python, WY. Oh, the Python interpreter in there. 462. So yet again, kind of surprised here. I was told Julia is way faster than Python. I was actually expecting Julia to just blow the doors off of Python. So interesting. So I learned some cool stuff about looping. I'll go ahead and check all this stuff in, and we'll just say git add. I do want to find some benchmarks where Julia is faster, adding loop benchmarks for Julia Python. So I guess a little bit of a surprise for Python here. All right. I think next week I can continue. Let's see. Yeah, keep going on here. So I'll go to the README here and say for week 7, maybe cover the exceptions. We'll cover exceptions and any file looping. All right. Well, thank you for whoever showed up, and we'll see you all next week.